A single cosmic explosion can outshine a billion suns. We are diving into the universe's most energetic events, titanic spectacles that shred the laws of physics as we know them. By the end of this journey, you will understand the fundamental forces that shape reality itself, revealed through 25 astonishing facts. We will see how stars die in cataclysmic supernovas, how black holes tear apart suns, and how collisions in deep space forge the very gold in your jewelry. What does it feel like to witness the universe's ultimate fireworks show? The sheer scale of this power is almost incomprehensible. Let's anchor it with our first fact. A supernova, the final, violent death cry of a massive star, can briefly outshine every single star in its host galaxy combined. For weeks, this single point of light can rival the collective glow of hundreds of billions of suns. This is not a gentle fading. It is a detonation of cosmic proportions. The engine of this cataclysm is a process called core collapse. For millions of years, a giant star, many times more massive than our Sun, has been fusing elements in its core, building a layered onion of ash. It starts with hydrogen, then helium, all the way up to iron. But iron is a dead end. Fusing iron does not release energy, it consumes it. So when the star's core finally becomes a ball of iron, the nuclear furnace at its heart suddenly shuts off. Without that outward push of energy, gravity wins instantly. In less than a second, the core, which can be as massive as our entire Sun, collapses inward at nearly a quarter the speed of light. The implosion is so violent, so energetic, that it rebounds in a shock wave of unbelievable force. That rebounding shock, coupled with a flood of neutrinos, blasts the star's outer layers into space in a titanic explosion. The numbers are staggering. In just a few seconds, a supernova can release more energy than our Sun will emit over its entire 10 billion-year lifetime. To visualize the aftermath, we look to the Crab Nebula, the expanding cloud of stellar debris from a supernova witnessed on Earth in the year 1054. That beautiful, intricate tapestry of gas, still expanding over 950 years later, is the ghost of that unimaginable blast, a permanent monument to a star's final, glorious act of self-destruction. Yet that staggering supernova is merely a firecracker compared to what comes next. Our second fact introduces the hypernova, a blast so profound it redefines the word explosion. If a supernova is a star's death cry, a hypernova is its scream, an event linked to the birth of a black hole and the most powerful electromagnetic blasts in the cosmos, gamma-ray bursts. The key difference lies not just in power, but in mechanics. While a regular supernova leaves behind a dense neutron star, a hypernova occurs when a truly gargantuan star, perhaps 40 times the mass of our Sun or more, collapses under its own weight. This star does not just implode and rebound. Instead, in a scenario called the collapsar model, its core collapses directly and completely into a black hole. But this is not a quiet formation. The star is spinning rapidly, like a cosmic top. As the core vanishes into the black hole, the surrounding material forms a swirling, superheated disk of debris, a frantic whirlpool of doomed matter. The immense rotational energy and magnetic fields of this system then focus and launch two narrow, opposing jets of material. These are not ordinary jets. They are relativistic, meaning the particles within them are accelerated to over 99.9% the speed of light. These beams of pure energy punch straight through the carcass of the star and blast out into interstellar space. It is this focused, lighthouse-like beam of extreme radiation, a gamma-ray burst, that we can sometimes detect from across the universe. The numbers are, again, almost meaningless. A single hypernova can release hundreds of times more energy than a typical supernova, with its jets concentrating that power into beams of unimaginable intensity. For a few seconds, if that jet is pointed directly at Earth, The hypernova's gamma-ray burst can outshine every other source of gamma rays in the entire observable universe. These events are so rare and so catastrophic that they are considered among the most energetic explosions to occur since the Big Bang itself, cosmic beacons marking the violent birth of a black hole from the ashes of a titan. Those focused beams from a hypernova are the key to understanding the universe's single most powerful flashes of light. Fact 3. Gamma-ray bursts are the most luminous electromagnetic events we have ever detected. For a fleeting moment, they can outshine everything else in the gamma-ray sky, including entire galaxies. We now know these bursts come in two distinct flavors, each with a uniquely catastrophic origin story. The long-duration bursts, lasting from 2 seconds to several minutes, are the ones we just described. They are the death screams of those rapidly spinning colossal stars, collapsing into black holes, their focused jets of energy acting like cosmic blowtorches. But there is another, even more exotic source. Short gamma-ray bursts, which blaze for less than 2 seconds, originate from a different kind of apocalypse. Picture two city-sized stars, each more massive than our sun, but crushed into a sphere only about 12 miles across. These are neutron stars, the incredibly dense remnants of supernovas. In a binary system, these two stellar corpses can spiral inward over eons, drawn together by the relentless pull of gravity. Their final dance is a cataclysm of unimaginable violence. In the last milliseconds before they collide, they whip around each other thousands of times per second, rippling space-time itself with gravitational waves. Then they smash together. This merger can create a black hole almost instantly, but in the chaotic moment of impact, a tiny fraction of their material is flung out at near light speed. This ejected material, rich with neutrons, undergoes rapid nuclear reactions, forging heavy elements like gold, platinum, and uranium in a process called rapid neutron capture. The collision also launches, once again, those narrow, ultra-relativistic jets. The energy release is almost beyond calculation. A typical gamma-ray burst, whether long or short, can release more energy in just 10 seconds than our sun will radiate over its entire 10 billion-year lifespan. To grasp that scale, imagine condensing the total energy output of a star, every single photon of light and heat it will ever produce from its birth to its cold, dark death, and releasing it all in the time it takes to draw a single breath. That is the raw, unfiltered power of the universe's biggest bangs. That focused power is the only reason we can witness such events at all. Fact 4. The relativistic jets of gamma-ray bursts are beams of matter and radiation moving at over 99.99% the speed of light. This is not just fast, it is physics pushed to its absolute limit. At these velocities, the laws of relativity warp reality. Time for particles in that jet slows to a crawl relative to us, and their energy is boosted to astronomical levels. The jet itself is incredibly narrow, often only a few degrees wide, like a laser pointer aimed from one side of a continent to the other. This intense focus is everything. It explains why a gamma-ray burst, which can outshine a galaxy, remains invisible to nearly the entire universe. The titanic energy is not sprayed in all directions like a supernova. It is concentrated into a pair of pencil-thin beams shooting from the poles of the dying system. If that beam is not pointed at Earth, we see nothing. Our planet would be just another dark spot in the cosmos, completely unaware of the cataclysm that just occurred next door. But if, by chance, we are looking directly down the barrel of that cosmic gun, we receive the full, undiluted fury of the blast. This is why we detect only a handful of gamma-ray bursts each year, despite them happening far more frequently across the cosmos. We are waiting for the universe to spin its roulette wheel and point a beam in our direction. The initial flash of gamma rays is just the beginning, the tip of the spear. As the jet plows into the surrounding gas and dust at nearly light speed, it creates a violent shock wave. This collision generates a longer-lasting afterglow that radiates across the entire electromagnetic spectrum, from X-rays down to radio waves. Astronomers treasure this afterglow. It is like the glowing embers of a firework, allowing them to pinpoint the burst's host galaxy billions of light-years away and study the physics of the impact for days or even weeks after the initial blinding flash fades. That fading light tells the story of the jet's journey, a luminous echo of the most focused energy, release in the known universe. The gold in a wedding ring or a computer chip carries the echo of a stellar cataclysm. This brings us to Fact 5, kilonovas, the cosmic forges where the universe creates its heaviest elements. We touched on neutron star mergers as the source of short gamma-ray bursts, but the collision itself unleashes a second, spectacular phenomenon. When those two ultra-dense stars finally merge, their impact does more than create a black hole and launch jets. It violently churns up and ejects a small but crucial fraction of their material. This ejected matter, a hot soup of neutrons and atomic nuclei, is the perfect crucible for the universe's most extreme alchemy. In this environment, a process called rapid neutron capture, or the R process, occurs at a staggering rate. Atomic nuclei are bombarded by a dense flood of free neutrons, allowing them to grow heavier and heavier in a fraction of a second, skipping over stable forms to create exotic, unstable isotopes. These then decay into some of the most valuable elements we know. A single kilonova event can forge hundreds of times the mass of the entire Earth in pure gold, along with vast quantities of platinum, uranium, and other rare earth elements. The 2017 detection of an event named GDW 170817 marked a historic turning point. For the first time, observatories detected both the gravitational waves, the ripples in space-time from the merging stars, and the flash of light, the kilonova glow, from the same cosmic source. It was a multi-messenger masterpiece, confirming that these collisions are indeed the primary cosmic factories for the heaviest elements in the periodic table. Every piece of gold jewelry is not just metal, it is stardust, refined in the most violent furnace imaginable. The aftermath of two dead stars smashing together at nearly the speed of light. But the universe holds engines of destruction that dwarf even these cataclysmic mergers, cosmic powerhouses that burn for millions of years. Fact 6 introduces the quasar, the monstrous heart of a young galaxy. These are not fleeting explosions, but sustained infernos, the most persistently luminous objects in the entire cosmos. At the core of a quasar lies a supermassive black hole, a gravitational monster with a mass millions or even billions of times greater than our Sun. Yet this black hole is not dormant. It is actively feeding a cosmic predator surrounded by a swirling feast of gas, dust, and even entire stars. This doomed material does not fall straight in. Instead, it forms a vast, flat, superheated whirlpool called an accretion disk. As the gas spirals inward at tremendous speeds, friction heats it to temperatures of millions of degrees, causing it to glow with a blinding intensity across the electromagnetic spectrum. The physics here is mind-bending. The gravitational energy released by matter falling into the black hole is converted, with incredible efficiency, into pure radiation. The result is a beacon so brilliant it can outshine every single star in its host galaxy by a factor of 1,000 or more. All this staggering light pours from a region of space no larger than our solar system. To visualize the scale, imagine a single light bulb, small enough to hold in your hand, that somehow produces more light than every street lamp, car headlight, and house light on the entire planet Earth combined. That is the impossible concentration of a quasar's power. And often, these systems do more than just shine. Like their smaller cousins in gamma-ray bursts, many quasars channel some of this ferocious energy into colossal, magnetically focused jets that blast out from the poles of the accretion disk, stretching for hundreds of thousands of light-years into intergalactic space. These jets are visible to radio telescopes, painting giant, ghostly lobes on the cosmic canvas. Quasars are the signatures of a galactic core in its most violent and energetic youth, a phase most galaxies, including our own Milky Way, passed through long ago. They are the universe's ultimate lighthouses, visible from the very edge of space and time, marking the locations where gravity and matter engage in a perpetual, dazzling dance of creation and annihilation. That brilliant, sustained light of a quasar holds a secret, one that depends entirely on our cosmic viewpoint. Fact 7. Blazars are quasars whose devastating jets are aimed like a spotlight directly at our planet. The physics is the same, a supermassive black hole feasting on an accretion disk and launching twin beams of relativistic particles. The only difference is geometry. For a blazar, we are staring almost straight down the barrel of one of those jets. This chance alignment transforms our perception of the object completely. Because the jet's material is moving at over 99% the speed of light, a relativistic effect called Doppler boosting comes into play. The light from the jet, already intense, is bunched up and amplified as it races toward us, making the blazar appear hundreds or even thousands of times brighter than it would from the side. This also means its brightness is not stable. As turbulent clumps of material swirl in the jet and collide, they cause violent flares. A blazar can double in brightness in a matter of hours, flickering across the entire electromagnetic spectrum from radio waves all the way up to the highest energy gamma rays. This incredible variability makes them some of the most dynamic objects we can observe, but their usefulness goes beyond their spectacle. Astronomers use blazars as cosmic lighthouses. The brilliant, steady beam of light from a distant blazar must travel across billions of light-years of mostly empty space to reach us. But that space is not completely empty. It contains a faint, diffuse fog of hydrogen gas known as the intergalactic medium. As the blazar's light passes through this cosmic fog, specific wavelengths are absorbed, leaving dark lines in the spectrum like a barcode. By reading this barcode, scientists can map the distribution and composition of the invisible matter that fills the vast voids between galaxies. So a blazar is more than just a terrifyingly bright beacon. It is also a precision tool, illuminating the dark scaffolding of the universe itself. The brilliant jets of a blazar are a warning sign of a monster lurking in galactic cores, but sometimes that monster reveals itself in a more personal and far more violent manner. Fact 8. Tidal disruption events are the gruesome spectacle of a star being eaten alive. This occurs when a star, through the chaotic dance of orbits, wanders perilously close to a supermassive black hole. The star does not simply fall in, it is torn apart by the black hole's immense gravitational gradient, the difference in pull between the side of the star nearest the black hole and the side farthest away. This difference is so extreme it overcomes the star's own gravity, the force that has held it together for millions or billions of years. The star is stretched, elongated into a long, thin stream of gas in a process physicists grimly call spaghettification. It becomes a noodle of stellar plasma. Roughly half of this stellar debris is flung away into the darkness on hyperbolic orbits, lost forever. The other half, however, remains bound to the black hole. It does not fall straight in, but instead forms a swirling, chaotic accretion disk around the event horizon. As this disk of shredded star material heats up through friction and collisions, it unleashes a tremendous flare of radiation, often peaking in the ultraviolet and X-ray parts of the spectrum. For a period of months or even years, this single event can outshine the combined light of every star in its host galaxy, a temporary beacon signaling a cosmic feast. These events are precious to astronomers because they act as a flare gun in the dark. Most supermassive black holes, like the one at the center of our own Milky Way, are quiescent, dormant giants, invisible because they are not actively feeding. A tidal disruption event suddenly illuminates this hidden monster, allowing scientists to study its properties and confirm its presence. By watching the light curve of the flare rise and fall, they can measure the black hole's mass and spin and understand the physics of how matter behaves in the most extreme gravitational environment imaginable. It is a catastrophic end for the star, but for science, it is a brilliant flash of insight. The star's violent end is not always the final chapter. Fact 9. Magnetars are neutron stars with the universe's most powerful magnetic fields. You recall that neutron stars are the incredibly dense remnants of supernovas, city-sized objects with the mass of a sun. A magnetar is a neutron star pushed to an even more extreme limit. Its magnetic field is not just strong, it is almost inconceivably powerful, a quadrillion times stronger than Earth's magnetic field and 1,000 times stronger than that of a typical neutron star. To grasp this scale, imagine a magnet so powerful that if one were located halfway between Earth and the Moon, it would wipe the data from every credit card on our planet. The field is generated by a dynamo of swirling, superfluid neutrons in the star's interior during its first chaotic seconds after the supernova. This magnetic energy is stored in a rigid crust of iron nuclei, a crust under unimaginable strain. The magnetic fields are so intense they literally twist and warp the star's solid surface. This creates immense stress, and eventually the crust cracks. These are starquakes, seismic events on a stellar scale. When the crust fractures, it releases a cataclysm of pent-up magnetic energy in a sudden, terrifying rearrangement of the field lines. The result is a giant flare, an outburst of X-rays and gamma rays that can, for a fraction of a second, outshine every other source in our galaxy. The most dramatic example occurred in December 2004. A magnetar named SGR 180620, located 50,000 light-years away in a distant part of the Milky Way, unleashed a flare so powerful that for 1/5 of a second, it was brighter than a full moon in gamma-ray light. The pulse of radiation, having traveled for 50 millennia, washed over our solar system. It was so intense, it actually ionized atoms in Earth's upper atmosphere, disrupting long-range radio communications and permanently altering our planet's ionosphere. From a distance greater than half the width of our galaxy, a crack in the crust of a dead star 20 kilometers across reached out and touched our world. A magnetar reminds us that even in the quiet corpse of an exploded star, unimaginable forces are still at work, waiting to crackle back to life with the power to reshape space itself. Our own sun is a constant reminder that cosmic violence is not confined to the distant universe. Fact 10. Solar flares and coronal mass ejections are our star's most explosive tantrums, events that bring the power of a hypernova right to our cosmic doorstep. While they pale in comparison to the universe's titans, their energy is still staggering, and their impact is profoundly personal. These are two distinct but often related phenomena, both born from the sun's tangled magnetic fields. A solar flare is first, a sudden, intense flash of radiation across the electromagnetic spectrum, from radio waves to X-rays and gamma rays. It occurs when magnetic field lines near sunspots become stressed, tangle, and then violently snap and reconnect. This magnetic reconnection acts like a cosmic slingshot, accelerating charged particles to nearly the speed of light and heating solar plasma to tens of millions of degrees in a matter of minutes. The energy released in a major flare is equivalent to millions of 100 megaton hydrogen bombs detonating simultaneously. But the flare is just the flashbulb. The real heavyweight is the coronal mass ejection, or CME. This is not just light, but a physical expulsion of the sun's atmosphere. Think of it as the sun itself coughing up 1 billion tons of its own superheated plasma, a seething bubble of charged particles and embedded magnetic fields launched into space at speeds that can exceed 5 million miles per hour. While a flare's light reaches Earth in just over 8 minutes, a CME is a slower, more massive tsunami of solar material that takes anywhere from 15 hours to several days to cross the Gulf. When it arrives, it does not arrive quietly. Our planet's magnetic field, our magnetosphere, absorbs the blow, compressing on the day side and stretching into a long tail on the night side. This interaction is what creates the beautiful auroras, the northern and southern lights, as energized particles spiral down our magnetic field lines and strike atoms in the upper atmosphere. But the beauty masks a significant threat. A direct hit from a powerful CME can induce massive electrical currents in our planet's crust and in our long power lines, potentially causing continent-wide blackouts. It can fry satellite electronics, disrupt global positioning systems, and cripple radio communications. The most famous example, the Carrington event of 1859, was so powerful it caused telegraph systems worldwide to fail, with operators receiving shocks and papers catching fire from the induced currents. Today, a storm of that magnitude could cause trillions of dollars in damage and take years to recover from. So while our sun seems steady and benign, it harbors a volatile temper, capable of unleashing storms that remind us how intimately connected we are to the violent heartbeat of our star. The Carrington event was a direct hit from a solar storm of almost unimaginable power. In late August and early September 1859, our sun was in a period of intense activity. British astronomer Richard Carrington, observing a large group of sunspots, witnessed something unprecedented. He saw 2 brilliant patches of white light flare from the sunspots and vanish within 5 minutes. What he had seen was a massive solar flare, the flashbulb signaling the launch of a coronal mass ejection. This particular CME was special, a perfect storm of speed and magnetic alignment. It raced from the sun to Earth in just 17 hours, a journey that normally takes days. When it arrived, the world witnessed the consequences. Telegraph systems, the Victorian-era internet, failed spectacularly across Europe and North America. Operators received severe electric shocks, and telegraph papers caught fire from the induced currents. Some found they could disconnect their batteries and still send messages, powered solely by the currents flowing through the Earth itself. But the most widespread spectacle was the sky. Auroras, normally confined to polar regions, erupted worldwide. They were seen as far south as the Caribbean, Colombia, and even close to the equator. Newspapers reported that the light was so brilliant in the Rocky Mountains that gold miners awoke at 1 in the morning, thinking it was dawn, and began making breakfast. The crimson and green curtains of light were so vivid that people could read newspapers by their glow at midnight. This was not a gentle light show. It was the visible signature of Earth's magnetosphere being violently assaulted and overwhelmed. The modern implications of such an event are sobering. Our world is now utterly dependent on a vast, delicate web of technology that the Victorians could not have dreamed of. A Carrington-level storm today would induce colossal currents in our continent-spanning power grids, potentially frying transformers the size of houses. These transformers are not stockpiled, they are custom-built, and replacing them could take months or even years. The resulting blackout could be continent-wide and last for an extended period, cascading through water, food, and communication systems. Our fleet of satellites, essential for global positioning, banking, and communications, would be bombarded by high-energy particles, with many suffering permanent damage. Estimates suggest the total economic impact could reach into the trillions of dollars, with a recovery measured in years, not days. The Carrington event stands as a stark reminder that the most energetic events are not always the most distant. Sometimes they come from our own cosmic backyard, a tempest from our life-giving star that holds the power to reset the clock on modern civilization. These brilliant flares and jets all point back to a single, monstrous source of power. Fact 12 introduces the family of cosmic engines known as active galactic nuclei, or AGN. This is the umbrella term for any galaxy whose core is dominated by a supermassive black hole in the act of feeding, unleashing tremendous energy. Quasars and blazars are not separate monsters, they are just different faces of the same beast, seen from different angles. Astronomers now understand this through the unified model of active galactic nuclei. The core components are always the same. At the center is the supermassive black hole itself. Surrounding it is a superheated, donut-shaped accretion disk of spiraling gas. Further out, there is often a thick, dusty ring of material called a torus, shaped like a cosmic bagel. And from the poles of the system, perpendicular to the disk, erupt those powerful relativistic jets. What we call the object depends almost entirely on our line of sight. Imagine you are looking at this cosmic machine from the side, edge on. Your view of the brilliant accretion disk is blocked by the thick, dusty torus. You might only see the faint glow of gas above and below the disk, or perhaps the jets shooting out sideways. This is what we classify as a Seyfert galaxy, an active core where the host galaxy's stars are still clearly visible around it. Now, tilt your viewpoint upward. If you look from an angle where you can see over the dusty torus and get a clear, direct view of the intensely bright accretion disk, you're looking at a quasar. The central engine is so luminous it drowns out the light of billions of stars in its host galaxy. Finally, imagine you have the luck, or perhaps the misfortune, to look almost directly down the barrel of one of the relativistic jets. In that case, the jet's amplified, Doppler-boosted radiation completely dominates the scene. You're no longer seeing a quasar, you are seeing a blazar, the most violently variable object in the sky. This unified model is a masterpiece of cosmic perspective. It tells us that the universe is not populated by dozens of different kinds of celestial monsters, but by one fundamental engine whose appearance is a simple trick of geometry. Whether we see a brilliant quasar, a flickering blazar, or a quieter Seyfert galaxy depends not on what the engine is, but on where we happen to be standing in the grand cosmic theater. This realization transformed our understanding, showing that the most energetic phenomena are connected by a single, elegant, and terrifyingly powerful blueprint. But those brilliant jets from an active galactic nucleus do not simply vanish into the void. Fact 13. Radio galaxies create colossal lobes of energy that dwarf their host galaxies entirely. These are a specific class of active galactic nuclei, where our view is from the side, giving us a perfect profile of the jets in action. The central supermassive black hole is still there, feasting and launching its twin beams of relativistic particles. But in a radio galaxy, we see the full, breathtaking aftermath. Those narrow, focused jets travel for hundreds of thousands of light years, far beyond the visible stars of the host galaxy. Eventually, they slam into the thin, diffuse gas that fills the space between galaxies. This is not a gentle stop. The jets plow into this intergalactic medium like a fire hose hitting a wall of smoke, creating a pair of massive, ballooning shock waves. These shocks are where the magic and the radio light happens. The impact accelerates electrons to nearly the speed of light, causing them to spiral around magnetic fields and emit synchrotron radiation, a brilliant glow we detect as radio waves. The result is two gigantic, often symmetrical lobes that bracket the host galaxy like ghostly ears. They are immense, faint, and incredibly ancient. A prime example is the famous Cygnus A, one of the brightest radio sources in our sky. In visible light, it looks like an unremarkable, fuzzy, elliptical galaxy. But when viewed through a radio telescope, its true nature is revealed. Two colossal lobes, each over 300,000 light-years across, erupt from its core. That means the entire structure, from the tip of one lobe to the tip of the other, is well over 500,000 light-years in extent, many times larger than the Milky Way itself. These lobes are not static. They are dynamic reservoirs of energy, constantly being fed by the jets and slowly inflating over cosmic time, pushing the intergalactic gas aside. They are cosmic weather systems, shaping their environment for eons. Studying their structure tells astronomers about the power and history of the jets, the density of the space between galaxies, and the long-term impact a single hungry black hole can have on its entire corner of the universe. While radio galaxies sculpt space with visible lobes, the universe also fires invisible bullets. Fact 14. Cosmic rays are subatomic particles, primarily protons and atomic nuclei, accelerated to nearly the speed of light. They are not rays of light at all, but a relentless, invisible rain of matter, a hail of atomic shrapnel constantly bombarding our planet from deep space. Every square centimeter of Earth's upper atmosphere is struck by several of these particles every second. Their origins have been one of the great mysteries of astrophysics for over a century. We know they come from outside our solar system, carrying with them a fingerprint of the incredibly violent processes that launched them. The leading suspects are the shock waves from supernova remnants. When a star explodes, the expanding shell of debris creates a massive, chaotic shock front moving through interstellar space. Charged particles can get caught in this turbulent magnetic field, bouncing back and forth across the shock wave, gaining a little more speed with each crossing until they are flung away at a significant fraction of light speed. But supernovas may only account for the lower energy cosmic rays. For the truly monstrous, ultra-high energy particles, we must look to even more extreme engines. The relativistic jets from active galactic nuclei or gamma-ray bursts are perfect candidates. Their intense magnetic fields and focused energy capable of accelerating particles to energies that defy belief. This brings us to the most extreme example ever recorded, the Oh My God particle. Detected in October 1991 by the Fly's Eye Observatory in Utah, this single subatomic particle, likely a proton, hit our atmosphere with mind-numbing force. Its kinetic energy was approximately 300 million times greater than the protons accelerated in the Large Hadron Collider. To put that in human terms, this one tiny particle carried the kinetic energy of a baseball pitched at 90 miles per hour. It was moving at such a preposterous fraction of light speed that, from its own perspective, the journey across our galaxy would have taken only minutes due to time dilation. The existence of such a particle poses a serious puzzle. According to theory, particles with that much energy should not be able to travel vast cosmic distances. They should interact with the cosmic microwave background radiation, the faint afterglow of the Big Bang, and lose their energy over a relatively short span of 100 million light-years or so. The Oh My God particle should not have been able to reach us from very far away, yet its trajectory pointed back to an empty void in space, with no obvious source like a nearby quasar or active galaxy. This means its origin is either something we have not yet identified, or our understanding of particle physics at these extreme energies is incomplete. These invisible messengers are a constant reminder that the universe's most energetic events are not just about light and heat, but about hurling the very building blocks of matter across the cosmos with the force of a cosmic cannon. That invisible hail of cosmic rays is a testament to matter pushed to its absolute limits, but the dead stars left behind by supernovas have their own violent secrets. Fact 15. Pulsar glitches are the sudden, unpredictable stutters in the heartbeat of a neutron star. A pulsar is a rapidly spinning neutron star, a lighthouse of the cosmos that beams radiation from its magnetic poles. As it rotates, that beam sweeps past Earth, creating a pulse of radio waves with a clockwork regularity that can rival atomic timekeeping. But sometimes, without warning, that cosmic clock skips a beat. The pulse's rotation suddenly speeds up, its spin rate increasing by a tiny but measurable fraction in a matter of minutes or hours before settling back into a slightly faster rhythm. This is a glitch, and for an object as massive and dense as a city-sized sun, a sudden change in momentum is a profound cosmic event. The leading explanation takes us into the bizarre quantum realm of the neutron star's interior. The outer crust, a rigid lattice of iron nuclei, is thought to be floating on an inner ocean of superfluid neutrons. A superfluid is a state of matter with zero viscosity. It flows without any friction at all. This neutron superfluid is also threaded with tiny whirlpools called vortices. Normally, these vortices are pinned to the crystalline lattice of the crust, meaning the superfluid's rotation is locked to the crust's spin. As the pulsar loses energy and its crust slows down over millennia, the superfluid inside wants to keep spinning faster, creating a rotational lag. Think of it like a spinning hard-boiled egg. The solid shell slows down due to friction with the air, but the liquid yolk inside keeps spinning freely for a moment. In a neutron star, the stress from this difference builds until it reaches a breaking point. Suddenly, millions of these pinned vortices unpin all at once, transferring a massive amount of angular momentum from the faster spinning superfluid to the solid crust. The result is a starquake, a seismic shift that makes the entire star shudder and speed up. Studying the recovery from these glitches is like taking an ultrasound of a stellar corpse. By measuring how long it takes for the star to settle after the glitch, astrophysicists can infer properties of the superfluid's friction, the rigidity of the crust, and the exotic states of matter at densities far beyond anything we can replicate on Earth. Each glitch is a telegram from the quantum heart of a neutron star, a fleeting signal that lets us probe the fundamental behavior of matter crushed into a realm where the rules of everyday physics cease to exist. While pulsars tick with a steady rhythm, the cosmos also broadcasts bursts of radio energy so brief they could be missed in a blink. Fast radio bursts are the universe's most mysterious millisecond signals, intense pulses of radio waves that travel for billions of light years, only to flare and vanish in less time than it takes your heart to beat. Discovered only in 2007, these blips are astonishingly powerful, releasing as much energy in 1,000th of a second as our sun does over 3 entire days. The challenge is their origin, a cosmic whodunit with several compelling suspects. The prime candidate ties back to the magnetas we just explored. A starquake on a magnetar's surface, a catastrophic rearrangement of its unimaginably powerful magnetic field, could theoretically produce a flash of radio energy bright enough to be seen across the cosmos. Another theory points to the cataclysmic mergers of neutron stars or white dwarfs, the same violent events that produce kilonovas and short gamma-ray bursts. But the plot thickened dramatically with the discovery of repeating fast radio bursts. Most of these signals are one-off events, a single scream in the dark. But a few sources have been caught firing off multiple bursts, sometimes sporadically, sometimes in frantic, predictable patterns. This repetition rules out any source that destroys itself in the process, like a merger. It points instead to an object that can survive its own outburst, something like a highly active young magnetar, perhaps one surrounded by a turbulent cloud of debris from a recent supernova. The repeaters have been a gift to astronomers because their recurring nature allows for precise localization. By patiently waiting for another burst from a repeater, scientists can use networks of radio telescopes to triangulate its position with incredible accuracy, pinpointing it to a specific galaxy billions of light years away. One famous repeater was traced to a modest, star-forming dwarf galaxy, a place where young, massive stars live fast. die young, and leave behind the kind of exotic corpses that could power such extreme flashes. Yet, even with these clues, the exact engine remains elusive. Some bursts show bizarre, complex structures within their millisecond span, suggesting intricate processes in their source. The hunt for fast radio bursts is now a forefront of astronomy, a race to catch these fleeting cosmic whispers and decode their message, a message that might be telling us about the most extreme magnetic fields in the universe or revealing entirely new classes of celestial objects. All those cataclysms, from stellar explosions to colliding corpses, are but echoes of a single, definitive beginning. Fact 17. The Big Bang was the ultimate energetic event, the origin of space, time, and all the energy we have ever discussed. It was not an explosion in space, but the explosive expansion of space itself from a state of infinite density and temperature. In the first fleeting moments, the universe was a seething, unimaginably dense soup of pure energy. One of its most dramatic phases is cosmic inflation, a concept where, for a sliver of time around 10 to the power of -36 seconds after the beginning, space itself expanded faster than the speed of light, doubling in size perhaps 100 times or more. This inflationary burst smoothed and flattened the cosmos, planting the seeds for all future structure, from galaxies to galaxy clusters. As expansion continued and the universe cooled, the energy began to condense into the first particles. By around 10 microseconds old, it had cooled enough for quarks and gluons to combine, forming a superhot, frictionless liquid known as the quark-gluon plasma. This primordial soup, trillions of degrees hot, filled the entire cosmos. For a brief window, the universe was a single uniform particle accelerator, a seething cauldron where the fundamental forces we know today were merged into one. The expansion and cooling continued relentlessly. After about 380,000 years, a monumental transition occurred called recombination. The universe had finally cooled enough for protons and electrons to combine and form stable, neutral hydrogen atoms. Before this moment, the cosmos was an opaque fog of charged particles where light could not travel freely. It was constantly scattered, absorbed, and re-emitted. But with the formation of neutral atoms, the fog suddenly cleared. The light, which had been trapped since the beginning, was finally set free. That first flash, that initial glow, has been traveling ever since, stretched and cooled by the ongoing expansion of the universe over the last 13.8 billion years. We detect it today as a faint, uniform microwave static coming from every direction in the sky. This is the cosmic microwave background radiation. It is the oldest light we can see, the afterglow of the primordial fireball, a baby picture of the universe when it was just a toddler. Its tiny, 1 part in 10,000 temperature fluctuations are the blueprints for everything that followed. The gravitational seeds that, over eons, would grow into stars, galaxies, and the titanic events that fill our night sky. Every hypernova, every quasar, every kilonova is a descendant of those first whispers of unevenness in the cosmic dawn. The faint afterglow of the Big Bang holds a secret, a clue that the universe's first moments were even more violent than we thought. Fact 18. Cosmic inflation was the universe's supersonic expansion, a burst of growth so extreme it defies all intuition. In the first sliver of time imaginable, around 10 to the power of -36 seconds after the beginning, something remarkable happened. The universe was not expanding at a steady rate. It was caught in the grip of a repulsive energy field, sometimes called the inflaton field. This energy acted like anti-gravity, causing space itself to stretch at an exponential, faster-than-light pace. To grasp this, think of a tiny patch of that primordial cosmos, perhaps 1 billion times smaller than a single proton. In less than a trillionth of a second, that patch inflated to become larger than our entire observable universe today. It was not matter moving through space faster than light, which is impossible. It was the fabric of space-time itself stretching, carrying energy along for the ride. This solves profound cosmological puzzles. Why does the universe look so similar in all directions? Distant regions on opposite sides of the sky have the same temperature, yet in a standard Big Bang model, they would never have been in contact to share heat. Inflation answers this by stating that these regions were once intimately connected in that tiny pre-inflationary seed, then stretched apart beyond the horizon. It also explains why the geometry of the cosmos appears so remarkably flat. Inflation would have smoothed out any large-scale curvature, like blowing up a balloon to enormous size and making its surface appear flat to a tiny ant crawling on it. But the theory makes a critical prediction. Such a violent, quantum-driven process would have created microscopic ripples in the fabric of space-time itself, gravitational waves that would leave a distinct, polarized pattern on the cosmic microwave background, like a signature etched into the first light. While that specific signature remains elusive, other evidence strongly supports inflation. The minute temperature fluctuations we see in the cosmic microwave background, the seeds for all galaxies, match the predictions of quantum fluctuations stretched to cosmic size during that inflationary burst. This means the largest structures in the cosmos, from galaxy clusters to the great cosmic web, owe their origin to quantum jitters magnified by the most energetic expansion event in history. Inflation was the ultimate power surge, a repulsive force so dominant it set the stage for everything that followed, determining the fate and shape of the entire cosmos in a blink of existence. That primordial energy from the Big Bang set the stage for environments where the very concept of a vacuum ceases to exist. Near a black hole, the fabric of reality is torn and rewoven by forces beyond our everyday experience. Fact 19. Pair production plasmas reveal how empty space itself can boil with particles in the shadow of a singularity. The principle comes from Einstein's famous equation: energy equals mass times the speed of light squared. It tells us that energy and mass are two sides of the same coin, interchangeable under the right conditions. In the crushing gravity and intense magnetic fields just outside a black hole's event horizon, those conditions are not just met, they are exceeded. The energy density becomes so unimaginably high that the void itself becomes unstable. According to quantum mechanics, empty space is not truly empty. It seethes with virtual particles, fleeting pairs of matter and antimatter that constantly pop into existence and then annihilate each other almost instantly. Normally, this quantum froth is invisible and undetectable, but near a black hole, the gravitational field is so powerful it can rip these virtual pairs apart before they can destroy each other. Imagine a wave of pure energy so intense that as it passes through what we call nothingness, it literally shakes particles into reality from the vacuum, like droplets condensing from saturated air. This is pair production. The most common pairs are electrons and their antimatter counterparts, positrons. In the frenzied environment around an active black hole, gamma-ray photons with energies millions of times greater than visible light can spontaneously transform into an electron and a positron. These newborn particles are born into a maelstrom. They're immediately caught in the black hole's immense gravity and whipped around by magnetic fields trillions of times stronger than Earth's. The result is a seething, super-hot plasma, a soup of charged particles and radiation, all created from what was ostensibly empty space. This plasma is not a passive bystander, it is a key player. Scientists believe this spontaneous creation of matter from the vacuum could be a fundamental power source for the relativistic jets screaming from active galactic nuclei. The intense magnetic fields near the black hole can channel and accelerate this plasma, focusing it into those narrow, lightning-fast beams that stretch for thousands of light years. In a very real sense, the most powerful jets in the universe might be fueled by energy extracted from the void itself, a testament to the bizarre marriage of quantum mechanics and gravity in the most extreme arena nature provides. This process turns the region around a black hole into a cosmic particle factory, where the lines between something and nothing are blurred beyond recognition. That boiling plasma around a black hole represents the pinnacle of known physics, but the cosmos still holds signals that mock our understanding. Fact 20. The WOW signal stands as one of the most tantalizing and unexplained bursts of energy ever recorded. On the evening of August 15, 1977, the Big Ear radio telescope at Ohio State University was performing a routine survey of the sky. Its computer, printing data on simple perforated paper, was programmed to log signal intensity on a scale from 1 to 9, with letters used for values above 9. For 72 glorious seconds, the telescope's fixed gaze swept over a patch of sky in the constellation Sagittarius. What came back was not the usual background hiss. The signal strength rose sharply, hitting a peak intensity recorded as 6 EQUJ5, before fading away in a perfect curve as the Earth's rotation moved the telescope's beam off the source. The sequence of characters, 6 EQUJ5, meant nothing to the computer, but when volunteer astronomer Jerry Aman reviewed the printout days later, he was stunned. He circled the alphanumeric string and wrote a single, emphatic word in the margin: "Wow." The signal's characteristics were precisely what scientists searching for extraterrestrial intelligence predicted a deliberate, narrowband transmission would look like. It was focused on the hydrogen line frequency of 1420 MHz, a natural cosmic channel that any advanced civilization might use to signal its presence. It was narrowband, meaning it occupied a very specific radio frequency, unlike the broad noise of natural cosmic objects. And most crucially, it exhibited the exact rise and fall in intensity expected from a point source passing through the telescope's stationary beam. It was a perfect candidate for an artificial signal from the stars. Yet, despite decades of follow-up observations by countless telescopes, the WOW signal has never been heard again. Its one-off nature is the heart of the mystery. All known natural cosmic bursts, from pulsars to the recently discovered fast radio bursts, are either repeating or can be linked to a visible cataclysm. The WOW signal remains stubbornly singular. Explanations have ranged from a passing comet, though none were in the right location at the time, to a reflected signal from human space debris, though the frequency used is protected for astronomy and the signal profile does not match. It simply appeared, shouted its 72-second message into the void, and vanished forever. It serves as a profound and humbling reminder. For all our catalogues of hypernovas and magnetas, for all our models of black holes and cosmic inflation, the universe may still hold energetic events we cannot yet categorize. Brief flashes of order in the radio noise that challenge us to keep listening, to stay curious, and to admit that some mysteries still pulse in the dark, waiting for their explanation. The WOW signal's singular whisper fades into the cosmic background, a reminder that energy can manifest as a fleeting, intelligent pattern. But the universe also orchestrates energy on a scale so grand, so patient, that it unfolds over cosmic eons. Fact 21. Galactic collisions are the slow-motion fireworks of the cosmos. We must recalibrate our sense of time and violence. These are not instantaneous explosions, but gravitational ballets lasting hundreds of millions, even billions of years. Two majestic spiral galaxies, each home to hundreds of billions of stars, are drawn together by their mutual gravity, beginning a dance that will utterly reshape them. The process is almost unimaginably slow from our human perspective, but the forces involved are titanic. The stars themselves rarely collide. The distances between them are so vast, but the immense clouds of gas and dust that fill each galaxy are not so lucky. They slam together. This collision creates immense shock waves that ripple through the interstellar medium, compressing vast nebulae and triggering a ferocious burst of new star formation, a phenomenon astronomers call a starburst. In these stellar nurseries, stars are born at a rate hundreds of times faster than in a quiet galaxy like our Milky Way. The most iconic example is the pair known as the antennae galaxies. Seen from our telescopes, they're a spectacular mess of glowing gas, brilliant blue star clusters, and long streaming tidal tails of stars flung out by the gravitational interaction, resembling the antennae of an insect. This chaotic beauty is the signature of a merger in progress. But the energy release is not just about making new stars. The galactic collision does something else, something that can awaken a sleeping monster. The chaotic gravitational forces funnel vast rivers of gas directly toward the center of the merging system. There, the supermassive black holes that once lurked quietly in each galaxy's heart are suddenly presented with a feast. As this gas spirals in, it forms a maelstrom of an accretion disk, heating up and blazing with the light of a newborn quasar. A galactic collision can literally turn on the lights in a galactic core, transforming a quiet neighborhood into one of the most luminous objects in the universe. This is the ultimate legacy of a slow-motion crash, a chain reaction where gravitational energy is converted first into a firestorm of stellar birth, and then into the focused, brilliant rage of a reignited black hole, a beacon that can shine across the universe for hundreds of millions of years. Those galactic collisions are the ultimate trigger for one of the universe's most prolific and violent star-making sprees. Starburst galaxies are cosmic factories where the laws of physics are pushed to their limit, birthing and destroying stars at a ferocious, unsustainable pace. In a normal galaxy like our own Milky Way, star formation is a gentle, steady process. In a starburst galaxy, it is a runaway explosion. These galaxies can form new stars at a rate hundreds, even thousands, of times faster than our own. Imagine if our entire galaxy compressed all of its star formation, spread out over billions of years, into a single frantic burst lasting just a few tens of millions of years. That is the scale of the frenzy. This incredible activity is often ignited by a gravitational shock, like the collision or close encounter of two galaxies, which sends vast waves of gas crashing together, compressing them into dense, fertile clouds where stars are born by the millions. But this prolific birth comes at a catastrophic cost. In these stellar nurseries, the most massive stars are born in abundance. These are the titans, the stars that live fast and die young. Because they are so massive, they burn through their nuclear fuel in just a few million years, a cosmic blink of an eye. Their short, violent lives end in spectacular supernova explosions. In a starburst galaxy, supernovas are not rare, distant events. They are commonplace, detonating with such frequency that they become a dominant force shaping the galaxy itself. Each supernova blast sends a shock wave tearing through the surrounding gas, heating it, compressing some regions to form even more stars, and violently dispersing others. Furthermore, the most massive stars, even before they explode, unleash torrents of radiation and powerful stellar winds. This combined energy from countless supernovas and raging stellar winds creates a phenomenon astronomers call feedback. It is a self-regulating, violent process. The very energy released by the newborn stars begins to blast away the gas clouds that formed them, eventually quenching the starburst and shutting down the factory. This feedback can sculpt the galaxy, driving vast outflows of material that enrich intergalactic space with heavy elements. We see these galaxies most clearly not in visible light, but in the infrared. The same dense dust clouds that are forming all these stars also obscure them, absorbing their visible light and re-radiating it as heat, making the entire galaxy glow like a cosmic ember in infrared telescopes. Starburst galaxies were far more common in the early, denser universe, and studying them is like looking back at the universe's wild, formative years, a time when galaxies blazed with the furious light of creation and destruction happening side by side. The universe's stellar furnaces can ignite in ways far stranger than a simple collapse. Fact 23 introduces the luminous red nova, a peculiar cosmic flare that is neither a supernova nor a classic nova, but something uniquely its own. These events are less energetic than a supernova's cataclysmic blast, but they far outshine the more common novae that occur on white dwarf stars. They are characterized by a distinct reddish glow and a relatively slow, smooth rise to peak brightness over weeks or months, followed by an even slower fade. For years, their origin was a genuine mystery, a new class of explosion without a clear engine. The leading theory, now strongly supported by evidence, points to a stellar embrace of the most intimate and violent kind, the merger of two stars in a tight binary system. Imagine two aging red giant stars, each having puffed up to enormous sizes as they neared the end of their lives, locked in a gravitational dance. Over eons, they spiral closer and closer, their outer atmospheres beginning to touch and tangle. This creates a shroud of common material that envelops both stars, dragging them into an ever-tightening spiral. Finally, their cores plunge together. This merger is not the hyperfast collision of two neutron stars, but a slower, more massive conflagration. The combined object briefly becomes a single, bloated, extremely luminous star shrouded in the dusty debris ejected during the merger, which gives the event its characteristic red color. The most compelling proof for this theory came from a star named V1309 Scorpii. Astronomers had been monitoring this variable star for years, noticing its orbital period was rapidly decreasing. Based on the merger model, they predicted it would merge and erupt around 2008. Remarkably, in 2008, it did exactly that. The star, previously invisible to the naked eye, flared into a luminous red nova, visible through small telescopes, its light curve matching the theoretical predictions for a stellar merger almost perfectly. It was a rare and beautiful validation, a cosmic prediction coming true before our eyes. Luminous red novas are the universe's slower, hotter size, the result of two stars ending their long cosmic dance, not with a distant orbit, but with a final, fiery embrace that lights up the galaxy in a deep, crimson blush. Our most terrifying energetic events may be mere sparks compared to what theoretical physics suggests is possible. Fact 24. Vacuum decay presents the ultimate cosmic catastrophe, a potential end to the universe that would make every supernova and gamma-ray burst seem trivial. This concept emerges from our understanding of the Higgs field, an invisible energy field that permeates all of space and gives particles their mass. According to our best models, this field might not be in its lowest possible energy state. Instead, our entire cosmos could exist in a metastable condition, a false vacuum. Think of it like a ball resting in a shallow dip on the side of a much deeper valley. The ball is stable for now, but it is not in the true lowest point. A sufficiently powerful nudge could send it rolling down into the abyss. In the cosmic sense, that nudge could be a random quantum fluctuation, a high-energy particle collision, or any event that concentrates enough energy in one tiny point of space. If such a trigger occurs, a bubble of true vacuum would nucleate. Inside this bubble, the Higgs field would collapse to its absolute lowest energy state, instantly rewriting the fundamental laws of physics within that region. The constants we rely on, like the speed of light or the strength of gravity, would cease to exist as we know them. Atoms would disintegrate, chemistry would become impossible, and the very structure of matter would unravel. The true horror lies in the bubble's expansion. The boundary between our false vacuum and the new true vacuum would expand outward in all directions at the speed of light. There would be no warning, no signal that could outrun the wall of annihilation. One moment, a distant galaxy would exist, governed by the familiar laws of physics. The next, it would be erased, replaced by a new reality with entirely different rules. A reality almost certainly incompatible with life, stars, or any structure we recognize. This is not an explosion of matter or energy. It is an erasure of the very framework that allows matter and energy to exist. The process would be unstoppable and inescapable, rewriting the cosmos from the inside out until nothing of our universe remained. While this is a highly speculative theory, and our universe has proven remarkably stable for 13.8 billion years, it stands as a chilling reminder. The most energetic event imaginable would not be a brilliant flash or a titanic collision, but a silent, light-speed transition from something to something else. A final, absolute end to every story the cosmos has ever told. Yet even the silent annihilation of vacuum decay would send out one final, ghostly messenger. Our 25th and final fact brings us to the search for ultra-high-energy neutrinos, particles so elusive they are called cosmic ghosts. Born in the heart of the universe's most violent events, from the cores of active galaxies to the jets of gamma-ray bursts, these neutrinos carry information no photon ever could. They are fundamental particles with almost no mass and no electric charge, which means they barely interact with normal matter. A neutrino can pass through a light year of solid lid without a single collision. This ghostly nature is both a challenge and a gift. It means they travel in perfectly straight lines from their source, undeflected by magnetic fields and unabsorbed by intervening gas and dust. They are pristine messengers, arriving at Earth with a story untarnished by their billion light-year journey. But catching one is like finding a single specific grain of sand on all the beaches of the world. To have any hope, scientists must build detectors of unimaginable scale. The most famous is the Ice Cube Neutrino Observatory, a telescope built not with lenses and mirrors, but with a cubic kilometer of pristine Antarctic ice. Buried more than a mile deep, thousands of sensitive light detectors are frozen in place, waiting. They are not looking for the neutrino itself, but for the extremely rare moment when one, against all odds, actually smashes into an atom of ice. That collision creates a secondary particle called a muon, which in turn emits a faint, telltale blue flash of light known as Cherenkov radiation. By mapping the pattern and timing of these blue flashes in the dark ice, scientists can reconstruct the neutrino's energy and, most importantly, the direction it came from. The hunt is for the highest energy neutrinos of all, those with energies millions of times greater than those produced in our most powerful particle accelerators. Each one is a smoking gun, a direct tracer bullet fired from a cosmic particle accelerator. When Ice Cube pinpoints one of these ultra-high energy ghosts and astronomers swing their telescopes to that same patch of sky, they often find the usual suspects, a flaring blazer or a distant, active galactic nucleus. This correlation confirms that these monstrous engines are not just brilliant beacons of light, but also powerful particle accelerators, capable of hurling matter itself across the cosmos at energies we can scarcely comprehend. These neutrinos are the final piece of the puzzle, a new sense with which to perceive the universe's fury. We have journeyed from the brilliant death of stars to the silent unraveling of reality, from focused jets that outshine galaxies to invisible particles that pass through planets. Each fact, each cataclysm, reveals a universe not of serene emptiness, but of continuous, breathtaking violence, a cosmic arena where energy is forged, focused, and flung across the void. These events are not just distant spectacles. They are the architects of our reality, forging the elements of life, shaping galaxies, and sending whispers of their power across the ages, waiting for us to learn how to listen. From the brilliant flash of a supernova to the silent unraveling of vacuum decay, our journey has spanned the full spectrum of cosmic fury. We have witnessed stars torn apart by black holes and galaxies colliding in slow motion, seen matter forged in neutron star mergers and particles accelerated in jets moving at the speed of light. Each event, from the familiar solar flare to the enigmatic fast radio burst, is a different expression of the same fundamental truth. The universe is a place of breathtaking, continuous violence. This violence is not random chaos, it is the engine of creation itself. It forges the elements that make up our world, shapes the galaxies that fill the void, and sends messages across the eons in the form of light, gravitational waves, and ghostly neutrinos. To study these events is to push at the very boundaries of human knowledge, forcing our laws of physics to account for energies and densities we can never replicate on Earth. They challenge our understanding of space, time, and matter, revealing a cosmos far stranger and more wonderful than we ever dreamed. So we turn the question to you. After exploring these 25 astonishing facts, which one reshaped your view of the cosmos the most? Was it the raw power of a hypernova, the patient terror of vacuum decay, or the mysterious whisper of the wow signal? Let us know in the comments below. And if you are hungry for more journeys to the edge of understanding, be sure to subscribe. Our next deep dive into the mysteries of space is already waiting.